When a fault occurs on a transmission line somewhere on the line, currents are flowing to ground. Measuring the direction of the flow of the ground current is used to assist some of the pilot-aided distance protection schemes in determining if the fault and the source of the ground current are located on their transmission lines. The ground directional overcurrent elements let the pilot-aided schemes know if the ground current rises above a minimum set level, and if it does, what direction the ground current is flowing. The ground directional overcurrent elements are used by the pilot-aided schemes because they are sometimes more sensitive to detecting faults than the distance elements are when the source has a weak infeed or high system impedance ratio. The benefits of using ground directional functions in pilot schemes are that the zero sequence and negative sequence currents that are used to detect the direction of ground currents do not contain very many load components. Therefore, the pickup levels for the ground directional elements can be set very low and thus are very sensitive. The ground directional elements are also very fast operating because the zero sequence and negative sequence currents build up from practically a zero pre-fault value. Also, since there was no ground current before the fault, the pre-fault zero sequence and negative sequence currents do not bias the direction of the developing fault components. There are two different methods of detecting the direction of ground current flow in the D60. These methods are the negative sequence directional overcurrent element and the neutral directional overcurrent element. Of these two methods, the neutral directional overcurrent element is more sensitive because the magnitude of the neutral current that is used for its directional calculations is greater than the negative or zero sequence currents that are used for the negative sequence directional overcurrent element. The advantage of the negative sequence directional overcurrent element is that it can be used to detect the direction of ground currents on paralleled transmission lines. The negative sequence directional overcurrent element has two separate independent functions, one for detecting ground current flowing in the forward direction and one for detecting ground current flowing in the reverse direction. When the element detects that ground current is flowing in the forward direction, it will turn on the operate flag that is called the negative sequence directional overcurrent 1 forward element. When the element detects that ground current is flowing in the reverse direction, it will turn on a totally independent flag that is called the negative sequence directional overcurrent 1 reverse element. When one of these two flags is on, obviously the other will be off. We will now configure and explain all of the settings to make the negative sequence directional overcurrent operate correctly. You must first configure the source of current and voltage that will be used to detect the direction of the ground current. The source you are selecting must have previously been set. A detailed description of this setting can be found on the GE Multilin UR Applications 1 Learning CD. The offset setting is only used when the transmission line being protected is a series compensated line. The type field lets you select which type of sequence currents will be used to detect the direction of the ground current. The two options are the zero sequence current and the negative sequence current. In most applications, you should select the zero sequence current for ground directional detection. However, if the transmission line we are protecting is a paralleled line, the mutual effects can make it difficult to accurately detect the direction of current flow. In this case, the negative sequence current should be selected because the mutual effects of parallel lines are minimized. The selected type of current used to detect the direction of ground current is often known as the polarizing current. The forward ECA setting stands for the element characteristic angle. This setting specifies the expected angle between the reference vector, which for this element is the negative of the negative sequence voltage, and the polarizing current at the time of a fault if the ground current is flowing in the forward direction. This was known as the maximum torque angle in electromechanical relays. The forward limit angle specifies as an angle how far from each side of the forward element characteristic angle the polarizing current can be to indicate the forward direction of ground current. If the zero sequence current or the negative sequence current you selected in the type field fall to the right of the line drawn by the forward limit angle, the negative sequence forward directional overcurrent flag will turn on. Making this angle less than 90 degrees will mean the polarizing current needs to be much closer to the forward element characteristic angle for the ground current to be recognized as flowing in the forward direction. The forward pickup setting defines the minimum amount of zero sequence or negative sequence current that needs to be present before the element will ever turn the negative sequence forward directional flag to on. Careful consideration needs to be taken when selecting this setting. because the D60 subtracts a small portion of the positive sequence current from the negative and zero sequence currents before using them for the directional calculation to eliminate erroneous signals caused by system unbalances, CT errors, and so on. When using the negative sequence current as the polarizing current, 12.5% of the positive sequence current magnitude will be removed before using it in the directional calculations. When using the zero sequence current as the polarizing current, 6.25% of the positive sequence current magnitude will be removed before using it in the directional calculations. For detecting the reverse direction of ground current, there is no reverse element characteristic angle to set. The reverse directional part of the element automatically uses the forward element characteristic angle transposed by 180 degrees. The reverse limit angle specifies how far from each side of the transposed forward element characteristic angle the polarizing current can be to indicate the reverse direction of ground current. If the zero sequence current or the negative sequence current you selected in the type field fall to the left of the line drawn by the reverse limit angle, the negative sequence reverse directional overcurrent flag will turn on. Making this angle less than 90 degrees will mean the polarizing current needs to be much closer to the reverse element characteristic angle for the ground current to be recognized as flowing in the reverse direction. The reverse pickup setting defines minimum amount of zero sequence or negative sequence current that needs to be present before the element will ever turn on the negative sequence directional overcurrent flag. Just like the forward directional pickup setting, a small portion of positive sequence current is subtracted from the negative and zero sequence magnitudes before using them for the directional calculations. The negative sequence current magnitude is decreased by 12.5% of the positive sequence current before using this value for protection calculations. As well, the zero sequence current magnitude is decreased by 6.25% of the positive sequence current before using this value for protection calculations. The neutral directional overcurrent element is the other D60 element that can be used to detect the direction of ground current flow, and also has two separate independent functions, one for detecting current flowing in the forward direction, and one for detecting current flowing in the reverse direction. When the element detects that ground current is flowing in the forward direction, it will turn on the operate flag that is called the neutral directional overcurrent forward. When the element detects that ground current is flowing in the reverse direction, it will turn on a totally independent flag that is called the neutral directional overcurrent reverse. When one of these two flags is on, obviously the other will be off. We will now configure and explain all of the settings to ensure the neutral directional overcurrent will operate correctly. You must first configure the source of current and voltage that will be used to detect the direction of the ground current. The source you are selecting must have previously been set. A detailed description for configuring the source can be found on the GE Multilin UR Applications 1 Learning CD. You will notice that below the source setting, there are several new fields that were not available in the negative sequence directional element. This is because in the neutral directional element, you have the ability to select either the zero sequence voltage or the measured ground current as the reference angle to make the directional comparisons. You are given this ability so that the neutral directional overcurrent element can still be used when the voltage transformers are delta connected. In the field labeled polarizing, you need to select which quantity to use as the reference vector. In this field, you can select voltage, current, or both. If you select both current and voltage to be the reference vector, the element will perform all directional calculations twice, once using the voltage and once using the current. If there is ever a discrepancy in direction between the calculations performed using voltage and the calculations performed using current, the neutral directional overcurrent element will turn on the forward directional flag. If voltage was selected as the polarizing quantity for the reference vector, you need to choose what to enter in the polarizing voltage field. You can use either the zero sequence voltage that is calculated from the phase voltages, or the measured zero sequence voltage that is read through the auxiliary input of the DSP module. If the measured voltage is selected, the auxiliary voltage input needs to be configured under the same sources as the phase voltage inputs. In the operating current field, you need to select which zero sequence currents will be used to compare against the reference vector. You can either select the zero sequence current calculated from the phase currents, or the zero sequence current measured by the DSP. Obviously, if the measured current is selected for the operating currents, the measured current cannot also be used as the polarizing vector. Therefore, if the measured current needs to be used as the operating current, the voltage must be used as the polarizing vector. The offset setting is only used when the transmission line we are protecting is a series compensated line, which will not be covered in this course. Notice that there is no type setting as there was for the negative sequence directional overcurrent element. The neutral overcurrent element only uses the zero sequence current as the comparison vector. The forward element characteristic angle setting specifies the expected angle between the reference zero sequence voltage and the polarizing current at the time of a fault, if the ground current is flowing in the forward direction. If current was selected as the reference vector in the polarizing field, the D60 automatically uses a forward element characteristic angle of 0 degrees because the ground current and the zero sequence currents should be the same. The remainder of the settings are the same as was described in the negative sequence directional overcurrent section. The POTT pilot-aided scheme stands for the Permissive Overreaching Transfer Trip Scheme, and like all other pilot-aided schemes, is used to speed up the clearing of faults that occur in the end zone of a transmission line. As for all pilot-aided schemes, a communication channel must be provided between the two relays located at each end of the transmission line for the POTT scheme to operate. In the POTT scheme, the remote D60 speeds up the tripping of an end zone fault by sending a permission to trip key from the remote D60 to the local D60 under two circumstances. The first reason that the remote D60 will send a permissive key is when it detects a fault occurring within its overreaching zone 2. This is where the expression overreaching comes from in the term permissive overreaching transfer trip. The second reason is an optional feature that can be used to make the remote D60 send a permissive key when it detects that ground current is flowing in its forward direction. Therefore, either the forward negative sequence directional overcurrent element or the forward neutral directional overcurrent element will send a POTT key to the local relay, as well as when the overreaching zone 2 pickup flag turns on. In the POTT scheme, the local D60 POTT logic will only cause the breaker to trip if it gets the PUTT key and the local relay has detected a fault within its zone 2 area of protection, or it detects the ground current is flowing in its forward direction if this function is enabled. Therefore, either the local D60's forward negative sequence directional overcurrent element or the forward neutral directional overcurrent element, as well as the picking up of a zone 2 fault, will cause the POTT scheme to trip the breaker if it receives a permissive key from the remote D60. Any combination of the two reasons the remote D60 sends transmit keys and the two reasons the local relay identifies a fault will isolate the transmission line and verify the fault is located on the transmission line we are protecting. As shown in Diagram 1, if Zone 2 of both relays identifies a fault, it is a clear indication that the fault is on the transmission line. In Diagram 2, the remote Zone 2 indicates that the fault is located to the left of the remote relay, and the forward flow of ground current as seen by the local relay indicates that the fault is to the right of it. Therefore, the fault is on the transmission line. In Diagram 3, the forward flowing ground current of the remote relay and Zone 2 picking up on the local relay is another clear indication that the fault is on the transmission line. Finally, in Diagram 4, the direction of ground current as seen by the two D60s shows the currents both flowing into the transmission line, which is a clear indication that the transmission line is faulted. Some additional logic has been added to the POTT scheme to add extra security to transmission lines that are connected parallel to other transmission lines. For example, if a fault had occurred on this parallel transmission line, the local and remote relays will operate in the following way. The remote D60 detects that ground current is flowing in the transmission line in the forward direction and will send a permissive key to the local D60 relay. The local D60 will detect that ground current is flowing in the reverse direction. This reverse ground over current detection does not meet the criteria defined by the POTT scheme, and thus the local relay will not trip. After a certain time period, the breaker on the parallel line will correctly trip to attempt to clear the fault. The ground current would now begin to flow through the transmission line in the opposite direction to feed the fault if the remote breaker on the opposite end of it did not open yet. The local and the remote D60s will now operate in the following way. First, the local D60 will have its forward negative sequence directional overcurrent element identify that the ground current is flowing in the forward direction. When the local D60 identifies the change in direction of ground current, The remote D60 will identify this change as well. However, due to the delay in the communication channel, the POTT permissive key will not immediately be removed. Since the negative sequence directional element of the local D60 indicates that the fault is in the forward direction, and the local relay is still receiving the permission key, the POTT scheme will cause the breaker to trip, shutting down the transmission line when it did not need to be. To overcome this problem, the POTT scheme has some additional logic to prevent this false tripping from happening. When the local relay now receives a permission to trip key from the remote D60, a timer begins to count. This timer now sets the maximum amount of time that the local D60 detecting forward flowing current will be allowed to trip the breaker. If this timer expires without the local relay detecting forward flowing ground current, the POTT scheme will not trip the breaker if forward flowing ground current is detected at a later time. The length of time that the forward flowing ground current will be blocked from tripping the breaker is also programmable by the user. The POTT scheme has added one more feature to help speed up the tripping of a faulted transmission line. If the breaker on the local end of the transmission line is open for any reason, the local D60 will not detect any current flow into the transmission line and therefore will not detect any faults within its zones of protection. If a fault did occur on the line, no key would be sent to the remote D60. If a fault occurred in the remote D60's end zone, the remote D60 will detect the fault in its zone 2 and send the POTT key to speed up the tripping of the local D60. The local D60 will not send a key because it does not see the fault in one of its zones of protection. Therefore, the tripping of the remote breaker will not occur until zone 2 of that remote relay has timed out. The additional logic in the POTT scheme, which is called the echo function, works in the following way. The local D60 must first detect that its own breaker is open. If its local breaker is open and it receives a POTT key from the remote D60, it will send the POTT key sequence it received directly back to the remote relay. The local D60 is telling the remote D60 that it is okay to trip because the local end of the line is already open and clearing of the fault will be much faster, ensuring the system will not become unstable. The remote relay will then take this echoed POTT key and immediately trip its breaker. If the echo function is going to be used, the line pickup protection element must first be configured. The description of the line pickup function will be covered later in the course. We will now go over the settings that need to be configured to have the POTT scheme operate correctly. As for all schemes, before the POTT scheme can be used in the relay, it must first be enabled in the function field. If you wish to use the echo function that was described earlier, you will need to set the permissive echo field to enabled. If you wish to customize the enabling of the echo function, select Custom in this field. The echo condition field needs to be set to tell the D60 under what conditions to echo the POTT keys it received if the permissive echo setting is configured to custom. The RX pickup delay field is used the same way as was described in the PUTT scheme section. The transient block pickup delay sets the time period after receiving the POTT key that the scheme will allow the local D60 relay, detecting forward ground, to trip the breaker. If this delay expires before the local relay detects ground current, the POTT will not signal the breaker to trip. The transient block reset delay will lock out the ability to trip on forward ground current once the POTT key has been removed. Once this timer has expired, any new POTT keys will allow tripping of the D60 on forward directional ground current. The echo duration field defines for how long the local relay will send the echoing of the POTT keys. The echo lockout field locks out the resending of the echoed POTT keys once the echo duration timer has expired. The line end open pickup delay sets the time period the local breaker must be open before the D60 will acknowledge the breaker open state and arm the echo part of the scheme. The seal-in delay is used to keep the outputs of the POTT scheme on long enough to trip the breaker. The function of this setting was covered in the DUTT section. The ground directional overcurrent forward field lets the POTT scheme know if the neutral directional overcurrent element or the negative sequence directional overcurrent element will be used to indicate the forward direction of ground flow. If both need to be used, a flex logic equation where the two operands are ORed together needs to be created and then used here. If you do not want tripping and keying to occur upon the detection of forward ground current in the POTT scheme, leave this setting to off. Just like the other schemes we described, the POTT scheme can detect if the fault is occurring on a single phase or on multi-phases. These communication bit settings need to be configured to let the D60 know what key sequence scheme is used. The setting of these fields was covered in the earlier sections. The hybrid POTT, or Hybrid Permissive Overreaching Transfer Trip Scheme, is a modification of the POTT scheme that adds an extra degree of security and also adds additional protection for transmission lines that have a weak in-feed source. The hybrid POTT scheme works in the very same way as the POTT scheme to speed up the clearing of end-zone faults. In this scheme, both a Zone 2 fault and forward-flowing ground current being detected by the remote D60 will send a permissive key to the local D60, thus allowing it to trip. The hybrid POTT scheme adds extra security by having the local D60 also monitoring for the detection of reverse ground current or a Zone number 4 reverse fault. If either reverse ground current is detected or a fault is picked up in Zone 4, the hybrid POTT scheme is blocked from tripping. The other addition that the hybrid POTT scheme has over the POTT scheme is the ability to trip on faults that are fed by a source that has a high source impedance, also known as a weak in-feed. When a fault occurs on the transmission line with a weak in-feed that is located close to the local D60, the characteristics of the transmission line will operate in the following way. The voltage measured by the local D60 will be very close to zero. The current flowing through the local D60 CTs will also not be very high. Therefore, the distance zones of protection will not pick up because the current will be below the current supervision level as was discussed in the zones of protection section. Also, the zero sequence and negative sequence current will be almost zero. Therefore, the forward and reverse ground directional overcurrent elements will not operate. Even though none of the D60 protection elements have picked up a fault, the faulted line still needs to be cleared. The hybrid POTT scheme clears faults in this manner by using the following logic. If the D60 detects that no forward or reverse directional overcurrent protection elements have picked up, and no faults have been detected in either Zone 2 or Zone 4, and the relay detects that the voltage has dropped close to zero, the hybrid POTT scheme identifies that this is a fault that is being supplied by a weak source. If all of these 5 conditions are met, the hybrid POTT scheme will force the D60 to trip the breaker if permission is received via a hybrid POTT key and the weak in-feed feature is enabled. If this feature is to be used, the line pickup protection element must be enabled and configured. The setting up of the line pickup element will be covered in a later section. We will now go over the following settings that need to be configured to have the hybrid POTT scheme operate correctly. As for all schemes, before the hybrid POTT scheme can be used in the relay, it must first be enabled in the function field. If you wish to use the echo function that was described earlier, you will need to set the permissive echo field to enabled. The echo condition field needs to be set to tell the D60 under what conditions to echo the hybrid POTT keys it received if the permissive echo field is set to custom. If you wish to use the feature that allows for the clearing of faults on transmission lines that are fed by a weak source, as was described earlier, you need to set the field labeled Weak In-Feed to Enabled. Just as in the POTT scheme, the transient block pickup delay sets the time period within which this local relay will be allowed to trip after receiving the hybrid POTT key. If this delay expires before the local relay detects ground current in the forward direction, the hybrid POTT will not signal the breaker to trip. The transient block reset delay will lock out the ability to trip on forward ground current once the hybrid POTT key has been removed. Once this timer has expired, any new hybrid POTT keys will allow tripping of the D60 on forward directional overcurrent. The echo duration field defines for how long the local relay will send the echoing of the hybrid POTT keys. The echo lockout field locks out the resending of the echoed hybrid POTT keys once the echo duration timer has expired. The seal-in delay is used to keep the outputs of the hybrid POTT scheme on long enough to trip the breaker. The function of this setting was covered in the DUTT section. The ground directional overcurrent forward field lets the hybrid POTT scheme know if the neutral directional overcurrent element or the negative sequence directional overcurrent element will be used to indicate the forward direction of ground current flow. If you do not want tripping and keying to occur upon the detection of forward ground currents in the hybrid POTT scheme, leave this setting to off. The ground directional reverse field lets the hybrid POTT scheme know if the neutral directional overcurrent element or the negative sequence directional overcurrent element will be used to indicate the reverse direction of ground current flow. If you do not want the hybrid POTT scheme to block operation of the scheme when reverse current is detected, leave this field to off. Just like the other schemes we described, the hybrid POTT scheme can detect if the fault is occurring on a single phase or on multi-phases. This communication bit setting needs to be configured to let the D60 know what key sequence scheme to use. The setting of these fields was covered in the earlier sections. The directional blocking scheme that is available in the D60 is one of the most popular types of teleprotection schemes used in distance applications today. The purpose of the scheme is to speed up the tripping of faults that occur in the end zone of a transmission line. As for all pilot-aided schemes, a communication channel must be provided between the two relays located at each end of the transmission line for the directional blocking scheme to operate. In the directional blocking scheme, the local D60 has an additional delay timer that is started by the detecting of a fault inside its Zone 2 area of protection, or the detection of ground current flowing in the forward direction. This timer is set considerably shorter than the normal Zone 2 delay. When this additional timer expires, the local D60 will trip the local breaker unless the local D60 receives a block message or key from the remote D60. The remote D60 will only send this blocking signal if it detects that the fault is located in its Zone 4 area of protection, or it detects that ground current is flowing in the reverse direction, both of which indicates an external fault. We will now go over the settings that need to be configured to have the directional blocking scheme operate correctly. As for all schemes, before the directional blocking scheme can be used in the relay, it must first be enabled in the function field. The RX coordination pickup delay is the additional timer that, when expired, will cause the scheme to trip if a block signal is not received from the remote D60. It is important to set this delay large enough to allow the remote D60 to detect the reverse direction of a fault and for the block message to travel over the communication channel. In order to eliminate the false tripping of a transmission line that is connected in parallel to another faulted transmission line, as was described in the POTT section, the transient block pickup delay and the transient block reset delay need to be configured. When a fault has caused the ground current directional element to pick up in the reverse direction for a time period longer than the transient block pickup delay, and the direction of current changes to the forward direction, the reverse direction flag will be held on for an additional amount of time as defined by the transient block reset delay. This allows for the D60 to ride through the directional swing caused by faults on an adjacent parallel line. The ground directional overcurrent forward field selects the directional overcurrent element that will be used to detect the forward flowing ground current. The ground directional overcurrent reverse field selects the directional overcurrent element that will be used to detect the reverse flowing ground current. The number of communication bits and the assigning of the directional blocking receiving bits that are used to communicate between the two D60 relays need to be configured. The assigning of these settings is covered in the DUTT pilot scheme section. We will now give an example of how to configure a pilot-aided scheme in the D60. We will continue from where we left off in the last example and use the same settings file. The values we previously used to set up our zones of protection are seen here. The pilot scheme we will be using for this example is the PUTT pilot-aided scheme. We will use the settings file from example 1. Go to Inputs, Outputs, Contact Inputs. Contact Input 1 is the receive key of the PUTT scheme. Change the ID setting for Contact Input H7A to Permission Received. Any name can be used here, but this name will give us a clear indication of the purpose of this input when reviewed at a later time. Keep the contact debounce time for H7A as 2 milliseconds. This will ensure that the input won't pick up for false contact signals. Change the events for H7A to enabled. This will give us an indication in the event report if this contact input is ever turned on or off. Then save these settings to the settings file and close this window. Enter the contact output settings as follows. Go to Inputs Outputs, Contact Outputs. The breaker we are using for this example has 2 trip coils. Therefore, we will assign 2 contact outputs to be able to trip this breaker. Change the ID setting for contact output H1 to Trip Circuit Breaker Coil 1. For contact output H2, change the ID setting to Trip Circuit Breaker Coil 2. We will assign the signal that operates these contact outputs later in the example. Contact input 4 is the transmit key for the PUTT scheme. For contact output H4, enter PUTT transmit for the ID setting. Again, any name can be used here, but this name will give us a clear indication later on what these contact inputs are wired to. As mentioned, only 1 bit will be used for permissive transmitting and receiving, so only transmit signal PUTT transmit bit 1 can be used. Assign this output signal, PUTT-TX1, to contact output H4 as follows. In the Operate area for H4, select the Flex Logic signal, PUTT-TX1. The seal-in should remain off, since we don't want the channel to seal in and lock up. Keep the events for H4 to enabled, so that we will get an indication in the event report if this contact output operated. Then save these settings to the settings file and close this window. We will enter the PUTT pilot scheme settings as follows. Go to Control Elements, Pilot Schemes, 1P PUTT scheme. Enable the function by setting the function to enabled. Keep the Rx delay at 0 milliseconds, since we already specified a contact debounce time of 2 milliseconds in the contact input configuration. Change the seal-in delay to 10 milliseconds to allow the scheme to have a minimum operating time of 10 milliseconds. Set the number of communication bits to 1, since we have only 1 channel available. Set the permissive signal RX1 to contact input H7A, which is our PUTT receive key, by opening the menu and selecting the input that was renamed Permission Received. Set the target to Latched, enabling the user to witness the scheme operation on the front panel display. Change the events for the scheme to Enabled, so that we will get an indication in the event report if the scheme has operated. Then save these settings to the settings file and close this window. We now need to configure some customized logic to control the tripping of our breakers. It is always good practice to create some different equations that are categorized by the different reasons to trip the breaker. We will then join these equations into one master equation, which will then trip our breaker. We will first rename our equations by entering a name in the ID field of the Virtual Output setting menu. Open Inputs Outputs, Virtual Output. Equation 1 will be our final master trip equation. Therefore, enter trip in the Virtual Output 1 ID field. Equation 2 will turn on whenever any ground distance zone operates. Therefore, enter ground trip in the Virtual Output 2 ID field. Equation 3 will turn on whenever any phase distance zone operates. Therefore, enter phase trip in the Virtual Output 3 ID field. Set the events fields for these 3 virtual outputs to enabled to allow these signals to be tracked in the event report. Save these settings to the settings file and close this window. We will now create these 3 equations. We will start with our ground protection equation, which turns on whenever a ground distance zone operates. Go to Flex Logic and Flex Logic Equation Editor. We will create our first ground trip equation as follows. Select Protection Element in the Type field of the first line. In the Syntax field, select Ground Distance Zone 1 Operate. Select Protection Element in the next line's Type field. Set the syntax as Ground Distance Zone 2 Operate. Copy and paste can be used to simplify entry. Select Protection Element in the next line's Type field. Set the syntax as Ground Distance Zone 3 Operate. Select Protection Element in the next line's Type field. Set the syntax as Ground Distance Zone 3 Operate. Now, OR these four signals together by selecting OR from the Type field. Select 4 inputs for the syntax field. Write this OR gate to the virtual output by selecting Write Virtual Output in the Type field. And write this to Virtual Output 2 by selecting Virtual Output 2 in the syntax field, which is now labeled Ground Trip. We will now create an equation which turns on whenever any of the phase distance zones operate. In the next empty line, select Protection Element in the Type field. For syntax, select Phase Distance Zone 1 Operate. In the next line, select Protection Element in the Type field. For syntax, select Phase Distance Zone 2 Operate. In the next line, select Protection Element in the Type field. For syntax, select Phase Distance Zone 3 Operate. In the next line, select Protection Element in the Type field. For syntax, select Phase Distance Zone 4 Operate. OR these four signals by selecting OR for the Type field. Select 4 input for the syntax field. Write this to the virtual output by selecting Write Virtual Output in the Type field. Next, select Virtual Output 3, which has been relabeled Phase Trip in the syntax field. Our next equation will be the master trip equation that will eventually trip our breaker. We need to list the 2 equations which were created earlier, plus any other reason we wish to trip the breaker within this equation. From the next line, select Read Virtual Outputs in the Type field. Select Virtual Output 2, which is our ground trip equation for the syntax field. For the next line, select Read Virtual Outputs in the Type field. Select Phase Trip On, which is our phase trip equation created earlier for the syntax field. Select Protection Element in the next line's Type field, and the syntax as Line Pickup Operate. This is a protection element that is used to trip the breaker and will be discussed in the next section. In the next line, select Protection Element as the type and set the syntax as PUTT Operate. This selects the operation of our PUTT scheme. We will now OR these 4 signals by selecting OR in the type field and for input for the syntax field. This will match the number of inputs in our equation. Write this to the virtual output by selecting Write Virtual Output in the type field and select TRIP, which is Virtual Output 1 for the syntax field. Then save these settings to the settings file and close this window. We will now assign the master trip signal to the 2 output contacts H1 and H2 as follows. Go to Inputs Outputs, Contact Outputs. Assign Virtual Output 1, which is our trip signal, to contact output H1 as follows. In the Operate area for H1, select the Flex Logic signal Trip On, which is Virtual Output 1. Also select this in the Operate area for H2. The seal-in should remain off for both contact outputs, since we don't want the trip to seal in and lock up, especially when using a recloser, which we'll discuss later. Keep the events for H1 and H2 to enabled, so that we will get an indication in the event report if these contact outputs ever operated. Then save these settings to the settings file and close this window. Now the D60 has the ability to read all of the needed inputs, perform all of the necessary distance zones and scheme protection calculations, and finally trip the relay's contact output based on the distance functions and PUTT scheme.